All right, now we're ready. Oh, we have to turn on the projector. Okay. Oh, I've got the test right here on top too.
Can you tell me what section number 5 came out of?
Number 5. Okay. On test 1, number 5 came out of I'm guessing about 2-3, but let me see.
Oh, here it is. Well, it talks about AX equals B. That system of equations.
Right. Okay. What goes in the first blank there? It says write the system of linear equations in the form of AX equal B, where A is a matrix, X is a column vector, and B is a column vector. Okay. Then use the Gaussian elimination to slove, which means solve, this matrix. I hadn't noticed that until right now. Okay. This matrix for X. Okay. So basically, all you do is write your matrix column vector equal column vector.
So this is the A1, 1.
Okay, wait, yeah.
1, 2, B1.
Okay, it wasn't 2-3, it's 2-2, I think.
B2, 1, B3.
Or it may even be 2-1.
See, I'm just trying to make sure that I
Yes.
understand that
Okay.
the X, well, I'm trying not to just go off of this problem, but kind of a general thing. So A would be like A1, 1, B2,
Okay.
1, A1, 2.
Go to page 45. Top of the page. There's a system of equations, only it has.
Yeah, that's exactly what I thought it was.
Right. So you write it as
In
the
that
thing below. Yeah, write it just like below there. A is a 2x2 matrix.
Yeah.
X is a 2x1 column vector. And equal B is a 2x1 column vector. And
That's the easy part. What's supposed to go in the X?
okay, X equals, then solve that matrix
For X.
for X. Find out what the X has to equal. And it says use Gaussian elimination, so basically you can go off to the side here and just do your Gaussian elimination of your augmented matrix and just do and get your answer.
So you augment it back together after separating.
Yeah, you go back and put them together. Just okay. The second part is just back up like we were doing.
So you just have a 2x3 matrix and then solve basically.
Yeah, right. Do row reductions and give what x1 is, x2 is.
I think what messed me up on that one was that big open blank. Like I didn't realize you're supposed to write the AX equals B.
Yeah, that's yeah.
Okay. So that one's easy peasy.
Right.
I got it now. It's just that answer form.
Right.
And then I think
8.
8. Something was throwing me off there. I'm not really exactly sure what. Use inverse matrix to solve the matrix equation.
Okay. Now
This is the same thing. No,
yeah, except now it says use the other. You could, of course, do Gaussian elimination. I wouldn't be able to tell, but the point here is that you actually do the inverse, which is 2-3, I believe it is. Yeah, inverse of a matrix.
That's where you augment with the identity matrix.
Right. That's how you start it. And
you go ahead and make that
sort of like, okay, on page 70. Okay. You first do the inverse of this matrix, which is a pretty easy process. The small matrix, you have this little tricks you can do. And then just like theorem 211 says, once you have the inverse, A inverse here, then multiply it by your B. And that should give you your X. Find the inverse of this, and then that inverse multiplied by B on the left, and that gives you the X, the solution.
Like I said, I think it was just kind of, well, with the first one, it was like the answer form
Right.
kind of threw me off big time, and
Yeah.
then I guess because this had similar with the X being
Yeah.
like that, I don't know, thought they were related.
The only difference here is the first one you can solve by Gaussian elimination, the second one says use inverse matrix. Which, of course, I can. Okay. That it?
Yeah, that's it. It really wasn't anything
All right.
crazy. I've already done everything else.
Yeah.
I just wanted to ask about those two.
Right.
Mainly the number 5 though.
Yeah. And that was just a form thing. Yeah.
Yeah.
Okay. Now, starting where we left off before, I believe we were on page 114, section 3.2, and the top of 114. That's where my mark is anyway. I hope that's where we were. Now, previous page, top of that page was elementary row operations and determinants. Just remembering. Of course, your matrices are always square, okay? You can't take a determinant of a non-square matrix. You can't, okay? But if you're starting with matrix A and doing a row operation to get to matrix B, an equivalent matrix, if you're interchanging two rows, you negate the determinant. If you're
multiply, you have to divide by that. Or, well, whatever you multiply by, you have to multiply
the determinant by that, right? Okay. And if you obtain B from A by adding a multiple of one row to another row, the determinants are the same. Exactly. Now, those are all with rows.
That all stuck pretty well.
Yeah. Now, where page 114 is doing, although that theorem that we just rehashed is stated in terms of elementary row operations, the theorem remains valid when the word column is replaced by the word row. So you can do column things. Now, that's only for the purpose of determinants. Those are true. You don't solve equations or systems. You don't go around interchanging variables and multiplying one. Yeah, you don't do that. But when you're dealing with determinants, the determinant, when you swap two rows, it's the negative of the determinant. When you columns. When you multiply a column by a constant, you have to multiply the determinant of the first by that constant. And when you it's crazy. But this is only when you're doing determinants. Okay? So elementary column operations in two matrices are called column equivalent, not row equivalent. When one can be obtained from the other by an elementary column operation. Okay? Here are some examples. It's so hard to read that way, and since I got so much bigger. Now these are determinants. These are not everything about the. Let me get this done. Determinant of 2, 1, negative 3, 4, 0, 1, and 0, 0, 2. Okay? Now.
Okay, so we're going to obviously want to switch column 2
Yes, exactly. And if you did that, what does that tell you about the determinant?
Determinant, you're going to do the negative whatever determinant you find.
Yeah, okay.
Do you denote that somehow, or do you just have to remember
Okay, what?
that you're going to have to make sure you write a negative for the determinant? I mean, you just write a negative out front.
Yeah, you can put it on either side, but since you were starting with that one, it's the negative of the determinant of that. And can you tell me what the determinant of that one is? The second one? What would be the advantage of doing what we just did?
Oh, it's a 8. Negative.
It's a diagonal matrix. I mean, it's a triangular matrix. So therefore, it's just the product of the diagonal. Yeah. Minus 8. You can get it here by choosing column 2, and doing that. That's in the negative position, right? And then that's 8 minus 0, so that would be a negative 8. So yeah, you can get it that way pretty easily. That way it's almost blatantly obvious. Okay. So
We like blatantly obvious.
yeah, very good. Though the other ones aren't either. All right. Now, one that's not quite as easygoing maybe as that one. Here's a matrix, a determinant of a matrix: 2, 3, negative 5, 4, 1, 0, and negative 2, 4, negative 3. Okay? Now, is there anything obvious that you can do to simplify that one a little bit?
Not really.
You're used to looking at rows, aren't you?
Well, you got a 0 in the right column, but I don't see how that does you any good.
Okay. All I said to make it easier, you don't have to make it super simple.
Oh, divide out a 2 from the first column.
Yes. Okay. So to make this true, this is equal to 2 times.
Whoa, 2 times?
Yeah.
Okay, so you do the...
You take a half of the. Yeah. Right. Right.
Okay.
2 times what? The determinant of. Oh, okay.
1, 3, 5, 2, 1, 0.
1, 3, negative 5. Yeah.
Yeah, negative 1, 4, negative 3.
Was that a 2, 1, 0? I didn't hear it.
0.
Okay. And negative 1, 4, negative 3. Yeah.
Whenever I change a column or something,
Yeah.
I always write that first.
Yes, exactly.
So I was sitting there writing down a column.
And I was waiting for you to say that, and I was going to write it too. And then you started going across. I went, oh, you're going that way. Okay.
See, I figured I'd confuse you.
Right. You succeeded. Okay. All right. In evaluating a determinant, it is occasionally convenient to use elementary column operations, and example 3 is going to try that as well. Okay. Let me go and erase all this. Is that okay? Okay. Here's our matrix A. They love A. Okay. Negative 1, 2, 2. I liked it the other day. You said this is the, what do you say, the X of equations or the alpha functions or something like that. X, yeah, okay. 3, negative 6, 4, and 5, negative 10, negative 3. And what we're asked to do is find the determinant.
Well,
I know, something just flipped, didn't it?
make sure you're connected well.
Okay. It's still there.
Yeah, it switches out.
I know, I'm plugged in well there. I think I am there too. Oh, I didn't check that one.
Seems to be okay.
Okay.
I don't know what the deal was.
It could be maybe I hit this thing and maybe it jiggled a wire somewhere in there.
Probably.
Okay.
Alright, so the only thing that I can see, or, well, 2 step, well, still 1, I guess. You can divide out a 2 from the middle column.
That sure looks like the only thing I can see too. So Okay, so the determinant of this is equal to 2 times the determinant of -1, 1, 2, 3, -3, 4, and 5, -5, -3. Okay, that sure doesn't seem to be a lot easier. But, I mean, we can do anything we want to. And it looks like to me add the two columns together. So actually, to begin with, we could have done 2 times column 1 added to column 2, and you would have gotten, you didn't even need to take out the 2, but you would have this is equal to 2 times the determinant of leaving the first column alone, -1, 3, 5, 0, 0, 0, 2, 4, -3. And what's the determinant of that?
It would be -9 times 6 or 20.
Choose a row or column, any one. Guess what one I want to choose?
The -1 probably. Oh, well, see, that's what I took.
0 times this.
Oh, 0.
Everything is 0.
Okay.
Yeah, right. So, yeah, that just comes out being 0. If you can get a 0 row or 0 column, the determinant's going to be 0. And you didn't have to factor out the 2 first. We did, but it's fine. It made it maybe easier to see that those were exactly opposite of each other. All right. Do you like Sudoku? Sudoku?
Yes, sir.
Yes. That is basically can be probably or developed by matrices. Okay, you know, I can never work them anymore because Karen gets the paper and does them first. You know, aggravating, huh? Yeah, she's fine. She likes doing it. She's a numbers person too. She's a statistician, so not purely. She's an epidemiologist, but she deals with statistics all the time. All right, so let's look at matrices and the 0 determinants. Seems like what we just did in example 3, wasn't it? Example 3 shows that when 2 columns on a matrix are scalar multiples of each other, the determinant of the matrix is 0. That is one of the 3 conditions that yield the determinant of 0. So we actually have 3. You know, sorry, I guess I ought to write it. Theorem 3.4 on the thing, because not everybody has a book. Huh?
Who said that?
Well, I did. I guess I ought to. Theorem 3.4, conditions that yield a 0 determinant. Of course, A has to be square. If it's not square, it doesn't have a determinant. Okay? So if A is square and any one of the following conditions is true, then the determinant of A is equal to 0.
Whole row of zeros.
Yes, the entire row or column is zeros.
Two columns are the same.
Okay? Yeah. Which all 3 of those almost are saying the same thing to me.
Well, really the last 2 are pretty much lead to number 1.
Right, exactly. When you do one elementary row or column operation. One row or column is a multiple of another.
You don't really do much column operations if you're not given determinants.
Yeah, if you're not dealing with determinants, don't do them, okay? But with determinants, yeah, you can.
That would mess with things.
Yeah, because then they're not representing equations well anymore, you know. Because they're not, you don't go around doing things like that. But if what you're looking for is a determinant, yeah, you have the flexibility to do them all. It's just like you don't have to just pick the row with the most zeros, pick the row or column with the most zeros, so you can go any way you want to through that determinant, and it should give you the same answer. All right, now, did you want to do this proof?
Probably good.
Okay. It says verify each part of the theorem by using elementary row operations and expansion of cofactors, which is sort of a big his way of doing it. But anyway, for example, if an entire row or column is 0, then each cofactor of the expansion is multiplied by 0. Okay, so when conditions 2 or 3 are true, it's probably a super good one, use elementary row or column operations to create an entire row. So basically,
It's just completely circular, just saying.
exactly. So this one isn't a great one, but you just show it that, just like we did, if either a column or a row is 0. In fact, that's what I'm doing most of the time when I talk about them. I'm giving a real shorthand of the proof, you know, not longhand or formal or something like that, but it's doing it. Because if you have that row or column of 0, just go down it and it's 0 times the cofactor, 0 times anything is 0. Okay, so done. And then the others, if they're the same, add the -1 to another. That doesn't change the determinant any. That makes the second one, whichever it is, equal to 0, and then you've got number 1. Or if it's a multiple of another, multiply with the opposite multiple and add them together, and you make a copy. So yeah.
I just want to make sure that whenever I go into a class where they're going to be wanting us to do proofs,
Yeah.
I know how to.
Right. This one, they basically just talk through it.
It can't really. Well, I mean, I guess you could write it out. But
Yeah.
We don't have it.
And they just show some examples, which isn't really a proof. Okay.
It has to be kind of an all-encompassing sort of thing.
Yeah.
You would be using like A11 and A21
Yeah.
and A31.
Right. Yeah. Yes. Okay. Do not conclude, however, from Theorem 3.4 that the only conditions that produce a 0 determinant. This theorem is often used indirectly. That is, you may begin with a matrix that does not satisfy the conditions of 3, 4, and through elementary row or column operations, obtain a matrix that does satisfy one of those conditions. And this next example is showing that. Okay, here's our new matrix A, which is 1, 4, 1, 2, -1, 0, and 0, 18, 4. Okay, look all over that thing, and there's nothing there to suggest any row or column or anything else is a multiple of any other row or column. Okay? So just because those three aren't met doesn't mean that it won't happen. In fact, you could expand this and take this determinant and show that it's 0. What I'm thinking they want you to do is do an either elementary row or column operation. What do you think an easy one would be?
Well, for this we would kind of want to get it into like an upper or lower, wouldn't we?
If you could get it that way, it certainly would be nice. So what would you do?
I would do 2 row 1 or -2 row 1 plus row 2.
Okay, sounds like a wiener to me. And that would be, and that will not change the determinant at all. Same determinant. And that would be 1, 4, 1. 0. Okay, -9. -2. And then you write down the bottom row, 0, 18, 4. And what do you notice? Well, yeah, but that's not sufficient.
I think you need 1 more.
No, but look at these 2 rows.
Oh, okay, so they're multiples.
They're multiples of each other. As soon as you see that, done. Then you go back to theorem 3, whatever it was, 3.3, 3.4, because one row or column. This is a row, is a multiple of the other. Done. 0.
Took 1 step. Ooh.
1 step to get that right.
I'll take it.
Yeah.
Oh,
All right.
they love to talk.
Yeah. In that example, you could have obtained the matrix with a row of all zeros by performing an additional elementary row operation. But why? I mean, you already got the multiple of the other to stop. Okay. Now, the following table shows the numbers of additions plus subtractions and multiplications plus divisions needed for each of the 2. Okay, I got to read back up and see. Light is glaring in my eye. You have now surveyed 2 general methods for evaluating determinants. Of these, the method of using elementary row operations to reduce the matrix to a triangular form is usually faster than the cofactor. Yes, the cofactor generally a pain. If the matrix is large, then the number of arithmetic operations needed for a cofactor expansion can become extraordinarily large. Okay? For this reason, most computers and calculator algorithms use the method involving elementary row or column operations. The following table shows the number of additions plus subtractions. That's what I was reading before. If you have a 3 by 3, guess what? Cofactor expansion is actually a little easier. 5 additions and subtractions, 9 versus 10 multiplications. So what? If you go up to 5 by 5, though, you have 119 plus 205. That's 324 steps of some nature. On the row reduction, you're still down at 75. So now you're significantly lower. 10 by 10 matrices, you're really close to 11 million operations, whereas row reductions, you're 600 or so. It's major easier to do the row or column operations. In fact, the number of additions alone for the cofactor expansion of an order n by n matrix is approximately n factorial minus 1. Why would they say approximately n factorial? Okay. Actually, they say is, so it's not is approximately, just is. Because 30 factorial is 2.65 times 10 to the 32. Even a relatively small 30 by 30 matrix would require more than 10 to the 32nd. I'll ask you my eye or something.
That's
Gracious,
a
water.
10 with 33 zeros?
Yeah, you got it. 32, yes. If a computer could do 1 trillion operations a second, it would still take more than 1 trillion years to compute the determinant of that matrix using cofactor expansion. Guess what? They don't use it, okay? Yet row reduction would take only a few seconds as opposed to 1 trillion years. When evaluating a determinant by hand, you sometimes save steps by using elementary row or column operations to create a row or column having zeros in all but one position, and then using the cofactor expansion. Excuse me. To create a row or column having zeros in all but one position, then using the cofactor expansion to reduce the order of the matrix by 1. So let's do it. Let's do a few of these. Here's our new matrix A. Okay. Man. -3, 5, 2. 2, -4, -1. 3's -3, 0, 6. All right. What might you choose to do first? What's that? Column 1. Add these together. Is that what you said? Row. Add those together or add the negative?
And then throw a negative. Well, to get, I don't know why. I was wanting to get a 1 in the upper left corner.
Okay. Okay.
Probably better to do something else.
Okay. The first thing that popped out at me, and just that it did, was you could divide this row by -3. And that would give you a 1. Now, remember, it doesn't have to be upper left anymore, okay? It's okay to, but on looking at it again, it's pretty easy to multiply 2 times this and add to that, 6 times this and add to that, and then you immediately get 2, and you have a -1 here, but that's plus minus, so that would be a 1 times, so that wouldn't be too hard either, okay? So, there's several ways you can go. It just depends on what you want to do. Or, I think the easiest, maybe now that I look at it, multiply 2 times this and add to that. Right? So that might be the easiest. I didn't even see that till right now. 2 times this. Now you could divide out of 3 first and then do it, and it'd be even simpler. But not a whole lot. But if all you're doing is finding the determinant,
Just do 2 column 1 plus column 3.
right. Okay. So let's do that. 2 column 1 plus column 3. And that'll be the new column 3. So this will be equivalent to the determinant of, I'm going to go and write the determinant down, -3, 5, oops, yeah. Let's just go back and do it the way we, -3 to -3, 5, -4, 0, and,
-4, 3, 0.
okay, -4, 3, 0, you say. Yeah, okay. Now we can find the determinant by using the third. And that, by the way, did not change the determinant. Okay, so this gives us the determinant of that would then be the position here is we're using that third row. The position is of the -3 down there is a positive position. That would be a -3 times the determinant of that, right? Okay, which would be a -1, right? Okay, so that would be 3. Is that right? Pretty easy. Okay.
And you have to. Is there any particular reason you chose to go off of -3?
To do what now?
To find the determinant, is there any reason you went off of -3?
Just because it had zeros. I look for the.
Because you would have to do that plus the determinant of that 0 and then plus the. Yes, okay, I get it now.
You find the row or column with the most zeros, and that's why we did that, to get 2 zeros there. That's why I chose that one. So therefore, we're going to use this one and expand it, and it will be this times that. And that's all, because these two will give you that.
I understand now.
Yeah. So always look for the row or column with the most zeros, and then if you can get a few more easily, do them. Okay. And then, yeah. Okay. So that leads then to 3 by 3 was just way too easy, wasn't it? So let's do example 6, which is a 5 by 5. Thank you. Okay. This would be a 2, 0, 1, 3, -2. Really, a disgusting part of it is it's so easy to miss one number in here. -2, 1, 3, 2, -1. A 1, 0, -1, 2, 3. Is it? Yeah. A 3, -1, 2, 4, -3. An ugly 3, goodness gracious. How did that happen? I think my thing wobbled on me a little bit. Okay, and then a 1, 1, 3, 2, 0.
I see a pretty promising column.
Okay.
Column 2 seems to be.
Column 2 sure seems like a good candidate to work with. And then what would you do from there?
Well, you could just take row 1, 2, 3, 4, add it to row 2 and 5.
Yes, that's exactly what I would do. So this is equivalent to, and both of those operations would not change the determinant any. So let's just go on and do the determinant because that's what we're looking for. And we're using row 1 is fine. So we're going to leave that alone. 2, 0, 2, 0, 1, 3, -2. Row 3 is, okay, 3 is fine. 1, 0, -1, 2, 3. Row 4 we're using, so that's fine. 3, -1, 2, 4, -3. I hope I copied it right. And we're going to change the other two. So row 2 becomes what?
1.
That's nice.
0.
That's nicer.
-5.
5. Ooh, wait. Okay. 6.
-4.
-4. Okay, I got sort of wobbly on some of my columns here. I hope that won't mess us up.
And then the last row 5, will be 4,
Wait, wait. Oh, yeah, wait, I'm sorry. I'm looking at the wrong one. 4,
0,
0, 5, 6,
negative
-3. 3.
I
Okay.
think I know which one I want to use.
Yes. Okay. And how would you start that one?
Be -1, right?
Okay. But let's see. Is it really a -1? Plus, minus, plus, minus, plus. Yes, it is a minus 1.
Okay, so you
It's
can
a
just
positive value.
plus, minus, plus, minus, plus.
Yeah. Any way you want to go. You could go to the right. Plus, minus, plus, minus. Plus, minus, plus, yeah. Any way you get there. It's legal. Okay.
All the ones directly opposite.
Yeah.
4 directions are going to be opposite sign.
Okay. Now that unfortunately leaves you with a
4 by 4.
4 by 4. So let's write that down. 2, 1, 3, -2. 1, 5, 6, -4. 1, -1, 2, 3. You lose that row. 4, 5, 6, -3. Oh man. Doesn't look too pretty, does it?
Well, the first row doesn't look just too bad. Or first column.
First column, and I think I like that one best of any of them. Actually, third row is pretty good too.
Yeah.
But the
I was
advantage,
thinking that you could do -2 row 1 plus row 4.
Right.
Get rid of the 4, turn that to a 0, and then you can do like a negative. I don't know. Just start working those to zeros.
the one nice thing that pops right up is
That has a negative already.
if you say keep this one, add these, that gives you a 0, and maybe keep this one, add those, that gives you a 0. 2 times this would make that a 0. 3 times that would make that a 0. So that might be an easy one to do because that one minus sign, you don't have to mess with other minus signs. You want to go that route?
Looks to be about the same.
Yeah. And what was the one you're saying?
I was saying, well, you just be eliminating stuff on that left side. So do double negative the first row plus the last row. That'll get rid of the 4. And then do a double negative of the second row to get a 0 in the first row. And then negative of the second row to give you the third. Get rid of the third row.
Yeah.
Or get rid of the 0.
Yeah. So
It's about the same.
yeah, I think so.
Just more negatives to keep up with.
Yeah.
And it's doing rows instead of columns.
Yeah.
We
So
can,
which way you want to go?
we can do it the column one with the negative one.
Okay. Using that -1 to fiddle with the others. So the -1 that's out there needs to stay out there. Okay.
It's in the doghouse.
And I guess we're holding our second column constant, 1, 5, -1, 5. And we're adding the 2 columns together, and that gives you a,
Well, let's see. We do column 2 plus column 1.
right.
Do you want to go ahead and just write out all of these, and we can do all 3 of them?
Let's, sorry, do what you just said. Column 2 plus column 1. Okay.
That would be a 3, a 6, a 0, and a 9.
Okay.
Alright, you want to go ahead and add multiples of this to columns
Yeah.
3 and 4?
Yeah. Let's do 2 column 2 plus column 3. Right?
So that would be 5
not liking this too much. Okay, say again. 0. Okay.
And the last one would be 3, column 2 plus column 4.
Sorry. Not coughing this time, sneezing. I mean, not sneezing this time, coughing. Okay. That would give us a 1.
0, 12.
And what?
And
12. Okay. All right, what position's this one? Plus, minus, plus, minus. So it'd be a -1 times a +1. I won't even write that down.
Wouldn't that just be a, oh yeah. You just, that's the old negative one we've been carrying around for a while.
Yeah. Okay. And then the next one would be a 1 plus 1, so I'm not even going to write that. And that would then be times what's left, 3, 5, 1, 6, nope, 6, 16, 11. I'm having trouble following. Huh? I know, it's doing some strange things.
It cuts off sometimes. It'll just cut off for a second and it'll come back on.
Yeah. And it seems to be, I'm always messing with the screen here, so I'm wondering if I'm about to have a short somewhere in here. Okay, 6, 16, 11. If I start frying, just don't pour water on frying grease. 9, say again?
I said, oh, just go find some eggs.
Yes, exactly. As long as you're hungry, okay? Okay. I'm going to actually, at this point, I think I'll just...
Alright, we can divide out a 3 from that first column, and also it's, yeah, it did it like 4 times.
Yeah.
But yeah, we can divide out a 3 from that first column.
Yeah. So this would then be
-3 out front.
a -3 out front, and then that would be a 1, 2, 3, 5, 1, 16, 11, and 16, 12. And now I would be real tempted just to do repeat the first 2 columns. 1, 2, 3,
Yeah, but we got it in
5, 16, 16. At this point, it seems like it's easy to do this. I just hope I haven't made a dumb error because these are some big numbers. Okay? So that's a -3 times 16 times 12. You're going to have to help me with that one. You got a calculator? That would be 12 times 12 plus 4 times 12, 144 plus 48 would be 192. Is that right? Okay. I think that's 192. 12 times 16 times 12, right?
Right. 192.
192. And then this one is 15 times 11, that's 165.
Okay, I see it. Alright. That would be 55 times 3, which would be what, 5, 1, 6.
Okay, wait one. Okay.
165?
Yeah, that's what I said, but I'm being a little sloppy here. I'm going to, we're adding these things. I wasn't making that real clear. 165. Okay. And I can do that one, 32. Is that right?
The 16 looks like a 1 and a 6. I was trying to it
Right.
was 2 for a second.
Okay. All right, so I'm going to get rid of those lines so they won't confuse me any further than they already have. And then we'll do our minus 48, right?
Right, minus
176. Is that right?
yeah.
Okay. And minus 120. Okay, is there any easy way to do these additions? 192 minus 176 would be
I can just
16.
key
Okay.
them all in if you like.
Okay, that'll be fine with me. This will be a 45, and this will be a minus 16. Minus 16 and plus 16 go out. So negative 3 times 45, that's still a huge number.
I got negative 135.
Is that what they got?
That is what they got.
Oh, look at them. So there wasn't any way to avoid some large numbers. We could have avoided as large as ours were. Let's see, which way did they do theirs? Yeah, they...
It did it a little different.
Yeah,
I think ours was fine though. It didn't just get too huge.
yeah. It's just that some of our numbers got big. They happened to choose a way that kept the numbers a little smaller, but still, you can't avoid
I
one
feel
thing.
like if you stay 16 and under, it's
Okay. Yeah, I often wish I could, but no, okay. Stay 16 or under. When you get old. Yeah. It was so nice when I was 16 or younger. Okay. 3.2 exercises. Any of the odds, 1 through 19. Maybe do a few of the smaller ones, but do a few that aren't quite so small. That's the end of the section. Yeah, do either 21 or 23 or both. Any of the odds 25 through 35. Okay. I would look at 37. It's a true false, but you read through and make sure you understand why it's whatever its answer is. And do any of the odds, well, either 39 or 41, or both. And then there's a proof, 43. Okay. Interesting. And then 45 is a pretty interesting one too. A guided proof, 47. And that's it.
Well, I mean, it's kind of the same thing.
What's that? I couldn't hear what you said. Oh. What's that?
I'm not sure how to do that.
Do what?
The number 43.
43?
Yeah. Because I see where the first part of the equal sign, the A11 plus B11 comes from. That makes sense. But then the last two rows or columns, I don't really understand.
Okay.
It seems to me like it should be
Okay.
A12 plus A12. Or it would
All right.
be 2
Okay.
A12.
Okay, remember these signs are your determinants. They're not adding you're not adding the matrices, you're adding the determinants of the matrix. Okay. So notice that the last two columns on both matrices are the same. Right. So if you were adding these, let's just take that first one. You'd have an A11, A22, A33 plus an A12, A23, A31, doing our writing over, scooting the columns over, plus A13, A21, A32. Minus, and then we do the back diagonals, whichever order you want to do it, 13, A22, A31, minus A11, A23, A30. So if you wrote them all out and did the matrix, writing those sums of the products, you would have 3 pluses and 3 minuses, so 6 sums of 3 products each. Do it for A, the first matrix, and then do it for the second matrix. And then what you'll see is that the let's start the setup of it, and when you get to the point, say, oh, okay, then we'll stop, and you can carry it on. This is long and arduous, but let's start writing them out. A11, A22, A33 plus A12, A23, A31. I'm mentally moving that column over, plus A13. It just drives me nuts when it does that. A13, A21, A32. Minus back diagonals, A13, A22, A31. Right? Minus again, A11, A23, A232, I believe it is. Yeah. Minus our last one. Sorry. A12, A21, A33. All right. Now, I don't know if you've noticed this before, but when one's set up like this, just like this, notice that you have, for your first entry, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. You have to have 1, 2, 3, second entry, 1, 2, 3, 1, 2, 3, 1, 2, 3. That makes sure you haven't gotten something, written something incorrectly. Okay, that's that one. Now we're going to add to that something very similar for the B's. So add to that, and it's a B11, and then these two are going to be just the same because those two columns are exactly the same, right? A22, A33, right? Those two columns are the same as you had before. So nothing's going to change there. Okay? So it's only the ones that start with, that end with a 1, you're going to change those from A's to B's. Plus A12, A23, B31. Exactly. Plus 13 not plus, B21 times B21. Yeah, these are multiplied.
You were saying plus, and I was writing plus.
Wait. Yeah.
It's in groups of 3.
Yeah, groups of 3. Within the groups of 3, they're multiplied, and between them are pluses. Okay. A32. Right. Minus. Yeah. Yeah. That one would be the one that changes it. A13, A22, B31. Yeah. I may have done a different order than you did, but those 3 are in there.
You went top right to bottom left.
Right.
I guess it doesn't matter.
It doesn't. It does not.
I didn't think so.
Just
Multiplication is
right. Commutative, right. Minus a B11, A23, A32, minus A12, B21, A33. Okay. And as you just noted, I hope, you're adding these things together, so this is A11 plus B11 times, and those are the same, A22, A33, and then factoring those out, that's going to be a plus A31 plus B31 times A12. So those are the same.
Okay, so it's just they factored out the A12 to A13
Right.
from the addition of A11 and B11.
Right.
And then that's how they got them by themselves while the other 2 are being added.
Right.
Okay.
Right. Yeah. And
that's a lot of 1 1 1 2 2 2 3
Yeah.
3 3 1 3 2.
right. Okay.
They expect you to do that a lot in some of the upper level classes?
I don't know. See, I wasn't a math major, so and that may have been one of the reasons. No, I really would. My skills are in math, but I just like science better than math because to me, I guess maybe partly, more applicable, and also to me, some of the stuff in math can be boring, whereas in science it all seemed pretty interesting, But I don't know, and probably part of that was my background and stuff too. It just seemed like science had more pizzazz to it, but it really doesn't. You go far enough in science, it's boring too, especially if you're proving, stuff. But to me, my favorite subject was chemistry, not physics. But my brother said, "You don't want to be a chemistry major at Georgia Tech." They had way more hours to graduate, and they required you to take German. I mean, it was so many horrendous things. He said physics has the best major there after industrial management, which is what he had gotten into.
Chemistry is still supposed to be one of the most difficult majors to major in.
Yeah, and it was mostly just because of the number of courses they had you take and that they forced you to take chemistry. Because back then, most of the chemists, a lot of the chemists had been German, so they wanted you to take German so you could read it. That kind of stuff's not important anymore. So I didn't need another hard subject to do from scratch. I like to do French because I'd had some French in high school, and it's not easy to speak, but we didn't have to speak it. We just had to translate and write and stuff. I was much better with that than I was trying to speak it.
I'm bad at English and even worse.
Yeah, and another language. Well, that was the thing when we tried to do a French lab where you listen to what the tape recorder, which wasn't great quality there, said, and you had to, do things to it. I said, to my teacher, I said, I don't think English is fast, because French is, blah, blah, blah. I mean, they spit it out. It and Japanese, I think, are the two fastest languages on the planet. And I said, I don't think English that fast, so how can I think another language that fast, because I'm Southern, But fortunately, yeah, in college, all they did was reading and translating and writing and that kind of stuff, and I could handle that. It was more analytical than it was the other. So. All right, you okay with that one then? Okay. How are we doing? Oh, no. I was looking at the wrong thing.
About 7 minutes.
7 minutes. Let's get started on 3.3, properties of determinants.
Start right off with an example.
Yes. In this section, you'll learn several important properties of determinants. You will begin by considering the determinant of a product of two matrices. So, here's matrix A. 1, negative 2, 2. 0, 3, 2. And 1, 0, 1.
Wow. Column 1 and row 3 look pretty awesome.
Yeah, exactly. And you're going, and B is 2, 0, 1. 0, negative 1, negative 2. And 3, 1, negative 2. Did I say that right? Yeah. Okay. Now, the first thing they're asking for is what is the determinant of A?
You want to add negative column 1 to column 3 and then take the determinant there?
It sounds, okay, negative column 1 to column 3.
Yeah.
Okay.
And then you
And
have
then that will give you a 0 here.
column, or
Row 3, yeah. That's perfectly great. A good choice. Or you could have done negative row 1 to row 3 and done column 1. Yeah. Either one.
Trying to get used to talking in column ways.
Right. Okay. So, whoops. This is a determinant, not a matrix. Whoops. Whoopsie. Okay. All right. And let me repeat what you said. Negative column 1 to column 3. And that's going to be the new column 3. So that's going to be a 1, 0, 1 stays the same. Negative 2, 3, 0 stays the same. And this will be a 1, 2, 0. Okay? And then that's going to be a pretty easy one to do.
There'll be a positive 1 on the outside.
Yep, a 1 on the outside times.
Negative 2, 1, 3, 2.
Say again?
Negative 2, 1, 3, 2.
Negative.
I was saying that smaller matrix, we're taking the determinant of it.
Right,
So
right.
that would be negative 4 minus 4, which is 0.
Minus 3.
Oh, minus 3, sorry.
But negative 4 minus 3 is minus 7, isn't it? Okay. Okay. Hope I did it right. Okay? Yes. Okay. Let's do the determinant of B. How would you want to go on this one? Huh?
How are we going to tackle that one?
Yeah.
Let's see. I think again, go with a negative 2 times column 3 plus column 1. And then that way you have the 0, 0, 1 for row 1.
Yeah. Negative 2 column 3 plus column 1. Okay, that will work. Another possibility would be maybe adding row 2 and row 3, and that would give you a 1 0. That would make
You have to negative row
1 0 0. Yeah, that'd be enough. I mean, none any better than the others.
I can see that one.
Okay. Want to go with yours then?
Yeah.
All right. So let's do it. And this will be a determinant. And we're 0, -1, 1, and 1, -2, -2. If I wrote it right. Okay.
0 4 7 for that first person.
0 4 7. That sounds reasonable. Yeah. Okay. And that is a +1 there too. So it's just the determinant of that. And that would be
4 minus -7, which is 4 + 7, which is 11.
11. Good deal. Okay. Now what we got to do is multiply the two matrices. So let's do AB. Been a while, huh? It's going to be a 3 by 3, right? Okay.
Rewrite these matrices real quick. I had to turn to the next page.
What's that now?
I had to turn to the next page. I gotta rewrite them.
Oh, okay. Oh, you're in a different book from me.
No.
No. Oh, your page. Okay. Yeah. I was just going to use them at the top, but let's see.
So that would be a 3 by 3 in the first slot. 1 1 would be 2 plus 6, which is 8.
Yeah.
Then the one below that would be 0 0 6.
Okay.
And the last one would be 2 plus 3, which is 5.
Okay.
Next one would be 0 positive 2 plus, that'd be 4. By that.
You're doing 2 1, right?
Yeah.
0, yeah, 2, and what do you say? 4, yeah, got it.
0, -3, so it'd be -1 below that.
-1, okay.
0 0 1 below that.
Okay.
Last but not least, 1 4 positive 4 would be 1.
1, right.
0 -6 -4 would be -10. Be 1 plus -2, which is -1.
Okay. Now we need to take the determinant of that one. Ooh, oh, 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 oh.
You don't like that?
Not my favorite. Okay.
That's a shame.
I think I'd be tempted to use that middle
-1.
row, yeah, use this, and 4 times row 2
Plus
is that,
row 1, and
and
then
1, and just add those two together. Let's see what happens there. 4 row 2 plus row 1. And we're going to be doing a determinant, so let's just go on and change that. We're using row 2, so that's going to be a 6 minus 1 minus 10. Okay. New row 1 would be
32.
right.
Rows 0 and -39.
Oh, how beautiful.
My favorite.
Yeah.
Numbers.
I can't. I'm so glad I chose this one. Okay. Row 2 plus row 3.
11 0 -10. -11.
Okay. Yeah.
Thank you, Dr. Fowler.
Yes, anytime. Okay, these two together will be a minus,
Break out a calculator for this.
that would be 32, that would be minus 342, right?
Negative 352.
52. Okay, I can't add. Okay, and then plus a 39, that would be 429, right?
I got negative 781.
Okay,
Because remember right, so you got a negative there. Oh wait, I didn't, and then multiplied by negative 1. And you get positive.
okay, but wait. These two produce a minus,
Right?
minus those two, which would be a plus.
See, that's what it is. So that'd be negative 352 minus a negative 39, 77. So negative 77.
Okay, and what do you get when you multiply these two together? Negative 77. So we see that, or at least this example, and I think it's going to hold true, that the determinant of a product of two matrices is the product of the determinant of those two matrices. And that's what we're trying to show.
Well, we've been out of time for like 5 minutes.
Yeah, I was afraid of that. But we'll begin next time with theorem 3.5, which says the very thing we just did, I think. If I haven't stopped and looked at it, but I think it was. Now, somewhere once upon a time I had my eraser up here.
You need an eraser?
No, I've got one. I just need to find it. There it is, I think.
Is that not it to your right, right beside your computer? The silver
There,
thing?
here it is.
Okay.
Yeah. No, that's the chalk holder.
Oh, I didn't know what that was.
Yeah. Well, that board over there, when I ever use it, which is probably